All right, guys. Welcome back to another YouTube video. So, of course, you guys know that the CAPE Unit 1 2023 paper uh was on Monday. And yeah, I do have the paper now in my possession. I mean, looking at the paper, it wasn't so bad, to be honest. It wasn't so bad, but they shocked us. They shocked us. They surprised us with questions that we weren't expecting per se. But I mean, if you understood the elementary stuff pertaining to like precisions and accuracy and those things, and know how to manipulate your equations and all of those fun stuff, then I believe that you would have done a tremendous job, you know. Right. So what we're gonna do now is to discuss what the difference between precision and accuracy is. All right. So in from my estimation, precision is the exactness, right, of a set of measurements, So, when it comes on to precision, or if we say that a value is precise doesn't mean it's accurate. It just means that it is more consistent in terms of the values that you're getting, right? So how exact the values are is pretty much what precision speaks to. And then now for accuracy, right? That speaks to, in a sense, how close the measured value is to the true value. So like every what you call it, every substance or every object per se has a true value, right? Think about the earth, it has a true value. Now, when you do take the measurement sometimes, you might get a value close to that, but it won't be the true value. Like it's very difficult for you to get the true value. Or in fact, you'll never get the true value because the instruments are not I would say sophisticated enough to give you such exact values. All right. Anyways, it continues and it says that table 1 shows 3 trial measurements which were made to determine the density of a material whose true value was determined to be 3.75 grams per milliliter. Now they say comment on the accuracy, and it says justify your answer. So in this case, first thing first, you should state that the true value, right, is not close to the measured value, or we could state it the other way around, right? So we could say that the measured values are not close to the true value. So therefore, the result is not accurate, right? But as we continue, they then ask us to comment on the precision of the results. When you look at the values here, you're seeing that they are within an exactness or a close range, among themselves. So for that reason, we can say that the measurement, in this case, is actually precise, because after measuring it once, measuring it twice, you're getting roughly the same thing. What generally causes a thing like this is some type of possibly systematic errors, right, in your experiment. So especially when you see your values have been skewed by a lot, Yeah. So it could be systematic error. All right, so we can say that the result or the result rather, are precise, since they are close to each other. All right. So that's what I would put for such answer. Okay. Of course, I mean, this is not the mark scheme, so obviously they might word the thing differently. So they then went on to ask us, sorry about that. They then went on to ask us about fractional errors. So they said to us that the formula is used to calculate the centripetal force for an object undergoing circular motion, where F is equal to mass times v squared over r. It says write an expression to determine the fractional error in F, given the fractional errors, or the fractional error in M, V, and R. So all of those measurements that we're doing there, they have some type of errors, all right? When you're dealing with fractional errors, you generally take the absolute error, yes, and divide it by the actual measurement itself, or the actual value, right? So this is how we would generally start off, by saying delta F, which just speaks to the absolute error. So this is the absolute error. And then now this is the actual value. Now, because this is like a fraction really, and also there's some multiplication involved, when we're adding up the overall fractional errors, or whenever we're trying to find the overall actual errors, you generally need to add them really. So let's take, for example, we're gonna have to add the absolute error, or the fractional error for the mass. So we have absolute error in the mass divided by m, right? We're gonna plus it now to let's talk about v squared. Now, because this is being squared per se, how we would have to find the absolute, or how we would have to find the fractional error, is that we have to take the coefficient, take the square and make it become a coefficient per se. All right, and then we're going to times that by the absolute error for the velocity, and then divide that by the actual value of the velocity. Then we plus it to the same thing here for the radius, right? So the absolute error in the radius divided by the value of the radius. So that is where your 1 mark would come into play. As you can see, it doesn't take a lot, or yeah. So that's why it values 1 mark really, right? I mean, this is something that you would have to, it's not one of the easiest things to explain sometimes in terms of how it is done, all right? But especially for like, if you have like a variable that is being squared or raised to some type of power, to find that fractional error, you have to take whatsoever is in the power and multiply it by the absolute error. Then you divide it by the actual value. So that's ideally what you would need to do. Question continues, and it says, an experiment is performed using the apparatus in figure 1. It says a small disk of mass m on a frictionless table is attached to one end of a string. The string passes through a hole in the table and an attached narrow or vertical plastic tube. It says a disk of mass big M is hung at the other end of the string. One student hold the tube, makes the disk rotate in a horizontal circle of a constant radius r, while another student measures rather the period. So here we have a system, circular motion type of question, all right? We're seeing that there's a mass attached here, And you know, once we have something moving in circular motion, there will be some centripetal force. All right. Now, mind you know, because the centripetal force is connected to the string in this case, right? Tension force in the string will obviously equal the tension force that is acting down as well. So you'd find that those two forces acting right there technically are going to be equal. We're going to show you that in a few seconds. But firstly, they said they want you to state two conditions that must be satisfied if a body is moving with uniform circular motion. All right. So for that answer, for that question, my answer would be that there needs to be constant speed, okay? So for the object to be moving in uniform circular motion, you find that the object has to be moving at a constant speed. Likewise, the object needs to be changing its direction, okay? So there has to be some form of changing in the direction of the body, all right? The main reason why the direction needs to be changing is so that we can give rise to velocity, and velocity would then give rise to acceleration, okay? Now, the question continues, and they say that they want you to show that the relationship between period M, the radius R, and the masses M and big M is given by the equation T is equal to 2 pi times the square root of small m times R divided by big M times G. So in essence, you have to then look at what is happening with the system, okay? And understand that there's aspects of centripetal forces involved per se, okay? So, you know, let's just recall something here quickly, right? Because the thing is accelerating, right? Because it's accelerating, and I would have established to you earlier that your centripetal force, really, which is the force acting towards the center, right? You know that's going to equal to force, mass times the acceleration, right? That's what the centripetal force is. But what is causing that centripetal force? Or what does that centripetal force, where did that centripetal force come from? That, by and large, is based on the tension that is in the cable below. All right, as you can see, the forces are really connecting with each other here. So you're going to realize that the weight that is acting down is going to equal to the mass times the acceleration. So let's just get back to that section. All right. So of course, according to Newton's second law, you know, net forces is equal to mass times acceleration. In this case, centripetal force. For that reason, the force that is giving rise to the centripetal force is associated with the weight that is acting vertically downwards. If you remember anything about the centripetal acceleration, you know that acceleration in this case is going to be v squared over r, okay? Then you should also recall that v is nothing more than 2 pi r over over the period. Now, because we're dealing with a complete rotation, that's the reason why we say that our speed, or linear speed, would be circumference times, well, circumference divided by the total time. You know, just like how you find speed, distance over time, that's where this comes from. That's where this comes from. So in a sense, we're going to take that and substitute it into this to come up with a small equation for the acceleration. So acceleration is going to equal to, we're going to substitute for v squared, or we're going to substitute for v. So that becomes 2 pi times r divided by t, yes? And of course, it's been squared. I'm also dividing by r. So let's just do the expansion a bit. So our acceleration here is equal to 4 pi square r square divided by t square times r. R cancels, it's the square. So we're there left with this. So let's take that now and substitute it into this equation. So we have mg is equal to m times 4 pi square over t square. We want to make t square become the subject. So we can do that quickly. So t square is going to equal to m 4 pi square. I think I'm leaving out something, yeah? So there's an r that needs to be here, right? So there's an r. Let's put it beside this. And then divide that now by mg. Okay? Let's just pretty it up a little bit. Or even before we pretty it up, so let's see if we can just pretty it up a little. So yeah, so let's just make t become the subject now. So to make t become the subject, we'd have to square root everything, right? So we're gonna have m over r, we're gonna have our 4 pi square divided by mg. And then, you know, obviously, we can find the square root of 4, which is gonna give us 2. So therefore, t is equal to 2 pi times the square root of m over r mg. Please, guys, I'm not doing this paper to make you feel more flustered or whatever, or to blame yourself and say, oh, you should have done, you should have did this, you should have done this or whatever. It's just to obviously just show you what the paper contains. So please don't let it stresses you out if you didn't get it correct. All right. So yeah, that is which question that now? I don't even know which question it is, but that's what you would have been required to do. Now, obviously, they like to give graph questions, right? And so the next part of the question would be for you to actually take into account what is happening in terms of the measured values that you have here. So it says that the experiment the experimental procedure was repeated using the same apparatus, and we would have measured the time period for 4 different masses of big M with fixed values of small m and r. All right, so there are certain things that we're keeping constant. So they want you to just quickly fill this out, give you a 2 marks right here. So I mean, even if you didn't do so well on the other part, you could get 2 marks. See? So this is 50. This is 25. This is 16.6. This is, you could even round it up, you know, to make it a bit better for you. Yeah, let's just keep it, let's just round it up a bit. Okay, so that when we're plotting those graphs, it doesn't give us hell. Regarding this one, I'm going to round it up as well. So this is going to give me 2. This technically is going to be 1. And I believe this one is going to be 0.6. All right. And then this is going to be 0. Roughly the same thing. And I think I probably should make it with this with the decimal points a bit, so that it we can have a proper spread of the data. Possibly it will be too close right here. It's going to be a bit too close because the next value is going to be 0.56, and if I round that up, you know how that go already. So let's just try something out here. So this would be the exact value. This one was 1.96. Okay, and then this one would be right. So let's see what we can do with these values here. Okay. Let's see what we can do with these values. So the next part of the question would be for you to actually plot a graph, right, of t squared versus 1 over big M. So this is your x variable, this is your y variable. All right, and that's a 4-mark question. And after that, they want you to use this equation and put it in the form of y equal mx plus c. So we could go ahead and do that right now, so that you guys can see what we mean. So taking this equation, t is equal to such and such. We want t squared, and we want 1 upon m. So to do that, we're going to times both sides, or we're going to square both sides rather. Yeah, honestly, guys, you know, when I was doing like CAPE, it was really hard to do the past papers, you know. It was really hard to do the past papers. Like it wasn't the easiest. But I don't know if it's because of maturity or whatever. But the past papers they're quite simple now. As in, they're not so challenging after all. Just looking back at them. All right, so square both sides, it'll become t squared. This becomes right, this becomes 4 pi square. Okay, square root is going to cancel the square here for this. So we're left with mr over big M over g. See? So ideally, you have the equation that you want, you know, you have the equation that you want. So it's just for you to kind of rearrange it a little bit to see exactly. So what we can do, so from here we can say, okay, t squared is equal to 4 pi square, okay, times mr divided by g. And then we, in a sense, say multiply by 1 upon m, where this thing here is now your x variable. This is your gradient, and this is your y variable. So it's now really in the y equal mx plus c pattern or equation. So that's what they wanted you to do. Now I'm going to pause it here for now, and then I'll plot the graph. I will pick up from there, all right? So stay tuned for more videos, guys, on the 2023 CAPE Unit 1 past paper question. Guys, don't forget to hit the subscribe button. Don't forget to comment and, you know, turn on your post notification bell. We are gonna we're gonna do some multiple choice papers as well, so that you guys can see how those papers are done. All right. So that's it for now. Cheers.